Hey everyone, and welcome to This Explainer. Okay, today we are diving into a seriously mind-bending reality of our universe. And we're going to do it by zooming way in on the tiny, squishy, honestly kind of cute 3D building blocks of physics to solve a massive cosmic mystery. We're taking some complex concepts and breaking them down so they make perfect sense. Our topic today? The physics of cosmic silence. Let's get into it.
Section 1. The Silent Explosion. Hollywood versus reality. Okay, let's dive right into this. We're starting off by busting a massive Hollywood myth. You know the one. You've seen it a million times, right? The epic space battle, the colossal explosions, that thunderous bass that literally shakes your seat in the theater. But physics, well, physics paints a very different picture. Imagine you're just floating out there in the vastness of space. Right in front of you, a huge, adorable 3D animated star suddenly goes supernova. It bursts into these beautiful, glowing colors. The flash is absolutely blinding, and the energy release is just off the charts. But listen, you hear absolutely nothing. No boom, no rumble, just complete, eerie silence.
So why exactly is space completely silent? I mean, it really messes with what our brains naturally expect, doesn't it? Down here on Earth, whenever we see a massive release of energy, like say lightning striking or a volcano erupting, we expect this huge wall of sound to just hit us. Our brains are intrinsically hardwired to link visual energy with loud noise. So what's the deal? What is the actual physics behind this cosmic mute button?
Section 2. Meet the sound wave. The microscopic journey. To really get what's happening, or I guess what isn't happening in space, we first have to look at what sound actually is. Sound is not like light. Light is an electromagnetic wave, meaning it can travel literally anywhere, even through a dead vacuum. It doesn't need any help at all. But sound is what physicists call a mechanical wave, and that means it desperately needs a physical medium to travel through. It needs stuff. Air, water, a solid object, it needs physical material to latch onto. Without that material, a mechanical wave just cannot exist.
And this brilliantly illustrates exactly how that mechanical wave works in action. Down here on Earth, when something makes a noise, an object vibrates. That vibration compresses the cute, squishy 3D air particles all around it. Then, those particles playfully bump into their neighbors, passing the energy along like a microscopic game of dominoes. Finally, that chain reaction reaches your ear. This whole compression and expansion thing is called a longitudinal wave. Picture a classic toy slinky being pushed and pulled. The energy travels horizontally right through the rings. It's a super physical mechanical process that relies entirely on these tiny particles crowded together and pushing off one another.
Section 3. Space. The empty vacuum.
So think of Earth as this crowded, bustling party of vibrating particles. Right now, in the air around you, there are quintillions of molecules in every single cubic centimeter just constantly bumping and rubbing together. But then we zoom out to space. Space is a vacuum. To put that kind of emptiness into perspective, out in the vast interstellar voids, you might only find 1 or 2 single hydrogen atoms in an entire cubic meter. Imagine just one lonely, cute little 3D particle floating out there in the massive dark void. It literally has no friends to bump into. The distance between particles is so insanely huge that they basically never interact, they never compress, and they simply can't pass along that energy. So the crucial point is really just a simple, undeniable equation of physics. Space is a vacuum, which means you essentially have 0 particles. Because you have no particles, you get no compression. And without compression, you have absolutely no sound. Even if the most massive explosion in the universe goes off right next to you, the energy has no microscopic dominoes to knock over. The sound simply has nothing to travel through.
Section 4. Math of the mute button. The speed of sound.
All right, we've talked about it conceptually, but let's actually prove why our lonely space particles can't do their job using the real math. It all starts with the fact that the density of space is practically 0. Density is just a measure of how much stuff is packed into a given space. Since there's hardly any mass out there in the vacuum, it feels a little weird to even try and do math with it. But keep that near 0 density in the back of your mind, because it's the absolute key to our formula here.
Here is the actual speed of sound formula. Velocity equals the square root of the bulk modulus divided by density. Let's break that down and explain it simply for a second. What is bulk modulus? It's basically how much a substance resists being compressed. Think of it like a material's stiffness. Steel is super hard to squish, so it has a high bulk modulus. A fluffy cloud? Super low. Now look at that denominator, density. We just established that the density of space is effectively zero. In math, when the bottom of a fraction gets super close to zero, the whole equation just kind of breaks down. Realistically, with near zero density and zero stiffness, because there's literally no material to compress, this mechanical wave equation completely fails. The math absolutely proves the silence.
Section 5. Hearing in the void. The exceptions.
Now, you might be wondering, wait, if space is totally muted, how in the world do astronauts talk to each other? And haven't we seen those news articles where scientists hear a black hole? Well, there are some pretty fascinating exceptions. First off, space isn't 100% empty everywhere. There are these giant gas clouds, nebulas, that actually contain enough tiny particles to form a super thin medium. So faint sound waves can technically exist there, but they're way too weak and the waves are too spread out for our human ears to ever pick up. To get around this, scientists use a super cool trick called sonification. They take electromagnetic data, like X-rays from a black hole, and mathematically convert it into artificial audio signals. So we're essentially translating raw physics data into sound. And as for astronauts, they hear each other just fine inside their suits in the space station because they literally bring their own medium with them, trapped pressurized air from Earth. For long-distance chats back to Houston, they rely on radio waves. And remember, unlike mechanical sound waves, radio waves are actually a type of light. They're electromagnetic. They don't need any squishy physical medium to zip right through the void. So it really all comes down to this. Space is silent not because nothing happens there, but because there's no medium to carry sound. It is a wildly active place, full of massive, violent events. Supernovas, colliding galaxies, black holes tearing apart planets. But without those tiny, squishy, bumping particles to carry the mechanical wave, all of that awe-inspiring action happens in absolute, profound silence. No particles, no vibrations, no sound. So I want to leave you with this final thought. The next time you're sitting in a movie theater, popcorn in hand, and a massive spaceship blows up with this deafening, seat-shaking roar, will you remember the physics? Will you picture those lonely, isolated 3D particles out there with absolutely nothing to bump into? I really hope this explainer gave you a fun, new way to look at our universe. Thanks so much for hanging out with me. Keep asking those big questions, and I'll see you